Hi everyone, I'm Firuza Enchilina. Starting with this video, I'll be talking about the fascinating and still unsolved problems of gravity. I'll also be offering solutions to these problems. The solutions are simple, very simple in fact. Those used to heavy, complicated math might push back. They may say, that can't be right, nature is more complex. They'll expect mind-bending mathematics, but let's not rush. Remember, the simplest ideas are often the most profound. So let's begin. Gravity is the most familiar force we experience every second, every moment. It keeps us grounded on Earth and governs the motion of planets and galaxies. It may seem like there is nothing mysterious about it, but the deeper we study it, the more surprises we uncover. Why do all objects fall with the same acceleration, no matter their mass? Why is gravity incredibly weak compared to the other fundamental forces, and yet it shapes the structure of the entire universe? Why does it only attract and never repel? Why can't we turn it off or shield it like we can with electric forces? And finally, why don't any of our current theories of gravity fully agree with quantum mechanics? After all, both are trying to describe the deepest level of reality. Gravity isn't just a force. It's a collection of puzzles that modern physics still hasn't fully explained. In this video, I'll walk you through 10 of the most surprising properties of gravity, the ones that remain unsolved. And in the videos that follow, I'll gradually uncover its true nature. Because gravity is far deeper and far stranger than it seems. The first property of gravity: equal acceleration for all objects. Imagine this. You drop a hammer and a feather. Intuition tells you the heavier one should fall faster, but nature does something very different. In gravity, all objects fall with the same acceleration. Mass, composition, structure, none of it matters. The result is always the same. Why does this happen? On one hand, the greater the mass, the stronger gravity pulls on it. But on the other hand, the greater the mass, the more the object resists acceleration. And these two effects perfectly cancel each other out. The result is something remarkable. Gravitational mass and inertial mass behave as if they are always strictly proportional to each other, everywhere we test it. As Richard Feynman noted in his lectures on gravity, in summary, the first amazing fact about gravitation is that the ratio of inertial mass to gravitational mass is constant wherever we have checked it. So what do you think? Is this just a coincidence or a deep property of nature? The second property of gravity: incredibly weak. Now here's something even stranger. Gravity governs the motion of everything in the universe, and yet it's the weakest interaction we know. Sounds like a paradox. It is. As Richard Feynman pointed out in his lectures on gravity, the second amazing thing about gravitation is how weak it is. Let's compare. Take two electrons. Between them, you have electric repulsion and gravitational attraction. How do they compare? You might be surprised. The electric force is stronger than gravity by about 10 to 42 times. That's not just a lot stronger. That's a number with 42 zeros. Imagine this. If gravity were just a little stronger, the universe would look completely different. If it were weaker, large-scale structures might never have formed at all. But the deeper question is this: where does this enormous number come from? We still don't have an answer. Paul Dirac once tried to find a kind of cosmic pattern. He noticed that the ratio between the age of the universe and the time it takes light to cross an atomic nucleus is always close to a similarly huge number. He proposed that this isn't a coincidence, that it's connected to the age of the universe and should change over time. This led to an even more radical idea. Gravity might not be constant. The gravitational constant could depend on the age of the universe and slowly decrease as the universe evolves. So the mystery remains. Why is gravity so incredibly weak and yet responsible for everything? The third property of gravity, a force you can't escape. Gravity is universal. It doesn't pick and choose. It doesn't care what you are made of, whether you have charge or what properties you have. If something has mass or energy, it's already part of gravity, and everything has mass or energy. No exceptions. That's what makes gravity unique. Electric forces act only on charged particles. Other forces are selective too, but gravity works on everything. Every particle, every field, every form of energy, all of it is involved in gravitational interaction. Gravity literally stitches the universe together into a single whole. But the deeper question still remains. Why is this force universal, with not a single exception? The fourth property of gravity, attraction only. There is another strange feature that's easy to overlook. Gravity always pulls. Always. It doesn't know how to push. In electricity, there are two types of charge, positive and negative. That's why you get both attraction and repulsion. But in gravity, there are no opposites, no negative mass, no opposing charges. Just attraction, no anti-gravitational charges, no balance of opposites, only pull. So why did nature choose this setup? Is this a fundamental property or the result of something deeper? And more importantly, even if we come up with an explanation, would we be able to test it? The fifth property of gravity. Why does gravity curve space? We're used to thinking of space as just a stage where everything happens. Empty, flat, unchanging. But gravity seems to bend that stage. Or doesn't it? And if it doesn't, then what's really going on? A beam of light passing near a massive object suddenly bends. A path that should be straight becomes curved. It's as if something is subtly distorting space itself. Or is it? Maybe it's not space that bends, but the light itself. So what should we even call a straight line if light itself is moving along a curve? What does all of this really mean? Does gravity actually do something to space? Or is this just a convenient way to describe what we'd observe? Maybe gravity only acts on matter and large masses influence other masses in such a way that it only looks like space is curved. And the key question, can all of this be explained in a way that anyone can understand, even a school student, without complex geometry? And even more importantly, can we design a clear visual experiment that shows what's really happening? Does space actually curve or not? If we can figure out that kind of experiment could answer that question, it might be the key to understanding one of the strangest ideas in modern physics, the sixth property of gravity. It affects time. Gravity does something even stranger. It affects the flow of time itself. According to general relativity, the stronger the gravity, the slower clocks run. So does that mean time passes a little more slowly on Earth than it does in space? Is that really what's happening? In modern physics, time is measured using atomic processes, specifically the frequency of radiation emitted by atoms. That's our standard of time. So if time slows down, gravity must somehow be changing those processes. And this is where the real mystery begins. The periods of atomic radiation are described by quantum mechanics. So does that mean gravity is influencing quantum processes? Or maybe gravity doesn't affect time at all. Maybe it only affects atoms. In other words, What if gravity changes certain property of atoms and that's why their emission frequency shifts? If that's the case, gravity might be easier to understand. A massive object wouldn't be changing time itself, but rather acting on other objects, including atoms. As a result, atomic frequencies would change near a large mass like near Earth or the Sun. So what actually happens to an atom in a gravitational field? Has anyone really thought this through? To answer that, we somehow need to bring quantum mechanics into our theory of gravity. And this is exactly where we hit the boundary between two theories that still haven't been unified. Is it possible to resolve this in a way that's truly clear without vague explanations? I'll talk about that in the next videos. The seventh property of gravity. Light can get it wrong. You'd think light is the perfect traveler. It should follow the shortest path between 2 points. But near massive objects, something strange happens. A beam of light passing near the sun gets deflected. And not just deflected, it bends by an angle exactly twice that you'd expect from a straight line picture along the same path. You might ask, how is that even possible? If a straight line is the shortest distance, why does light seem to ignore it? According to Fermat's principle, light doesn't follow the shortest path. It follows the path of least optical length. And in a gravitational field, these two are no longer the same. But then an even sharper question comes up. Why exactly a factor of 2? Not 1.5, not 3, but exactly 2. Is it just a coincidence? Or is there a deeper law behind it? Something we still only partially understand. Here gravity and light together are pointing to something far more fundamental than it first appears. And we're definitely going to get to the bottom of it. The H property of gravity, a universe with zero balance. Now here's one of the most surprising ideas. It seems that the universe might have a zero total energy. On one side, there is ordinary energy, mass, radiation, motion. On the other, there is gravitational energy, which is negative. And according to our best understanding, these two contributions perfectly cancel each other out. So, in total, you get zero. This idea was discussed in detail by Richard Feynman in his lectures on gravity. Here's how he put it. With this estimate, we get the exciting result that the total energy of the universe is zero. Why this should be so is one of the great mysteries and therefore one of the important questions of physics. After all, what would be the use of studying physics if the mysteries were not the most important things to investigate? How is that even possible? All the energy in the universe and suddenly it adds up to zero. This doesn't look like a coincidence. It's as if the universe is somehow perfectly balanced from the very beginning. And that leads to even deeper question. Is this exact balance a fundamental law or the result of finely tuned initial condition? And if there is such tuning, who or what set it up? And most importantly, can we test this idea experimentally? If this isn't just a coincidence, it might be a key to understanding the origin of the universe itself. The ninth property of gravity, a force outside the quantum world? There is a problem people don't often talk about directly. At the foundation of modern physics lies quantum mechanics. At the deepest level, the world is governed by the uncertainty principle. That's fundamental. But here is the paradox. Gravity seems to live outside the world. Neither Newton's law of gravitation nor general relativity includes quantum uncertainty at its core. It's as if one of the fundamental forces of nature is ignoring the central principle of modern physics. Richard Feynman pointed this out clearly in his lectures. Finally, let us compare gravitation with other theories. In recent years, we have discovered that all mass is made of tiny particles and that there are several kinds of interactions, such as nuclear forces, etc. None of these nuclear or electrical forces has yet been found to explain gravitation. The quantum mechanical aspects of nature have not yet been carried over to gravitation. When the scale is so small that we need the quantum effects, the gravitational effects are so weak that the need for a quantum theory of gravitation has not yet developed. On the other hand, for consistency in our physical theories, it would be important to see whether Newton's law, modified to Einstein's law, can be further modified to be consistent with the uncertainty principle. This last modification has not yet been completed. And it still has not been made. Why? Because modern physics still doesn't fully understand the truly nature of gravity, the tenth property of gravity, a quantum theory that could explain everything. Now we come to the most intriguing part. All these strange features of gravity are not separate mysteries. They come together as pieces of a single picture, one that is still hidden from us. Step by step, we'll figure out why inertial and gravitational mass always match. We'll understand why gravity is so weak. We'll see why it acts on everything without exception and why it only attracts. We'll break down what curved space really means and what's actually going on there. We'll explore how gravity affects time through atomic processes described by quantum mechanics. We'll even calculate the bending of light using Fermat's principle, uncovering its simple and deep physical meaning, and see that it's one of the most fundamental principles in nature. But the real turning point is ahead. We'll arrive at the idea that gravity is rooted in quantum uncertainty. And if that's true, then gravity isn't just compatible with quantum mechanics. It has a quantum nature itself. Even more, we'll understand why the total energy of the universe is exactly zero, and in doing so, we'll be addressing one of the greatest mysteries in physics, as Richard Feynman once emphasized. This was Firuza Chilina. Subscribe, leave a like, and as always, the most interesting part is still ahead.